Hello, everyone. Thanks for having me here. I'm Sam Pollard, and this is work. I'm presenting a work done at Sandia Labs. Many co-authors, so thanks to all of them. They've been working on this project for years, and I've joined in more recently to write up and help with them. So yeah, this is a sound verification framework for Statecharts and their implementations. So I'll give some context to Sandia Labs. We're a US government research and development center. One of the things that we do is develop software for very high consequence embedded control systems. And in this case, the situation we're working in, the cost for errors is very high, and these systems are relatively simple. So this is a good use case for formal methods. I'll talk a little bit about, I can't go into detail about our systems, but I'll talk about some of the features that we're working with. We have asynchronous interacting components. For example, we have many systems communicating across a bus, different clock domains. We have requirements documents that are written in English and in formal diagrams. Think Visio and Microsoft Word, actually. These are modeled in MATLAB Stateflow. Now, Stateflow is used for many different things. I don't exactly know, but think of Stateflow instead as an abstract graphical modeling language for these systems. And then we have an implementation in C, which interacts with hardware. And from these, we require proofs of the system level properties, which is key, which is to say properties which hold across all of the systems interacting with each other. So some of the fortune we have here is we have strong control over the structure of the C programs, which allows us to set how the developers write. And we also have interaction with the system engineers, who are the ones making the Stateflow models. Now, there's a long history of verification, I'm sure, of models, as I'm sure you're aware, TLA, SMV, and as well as implementations directly. For example, Microsoft SLAM project with C device driver verification. However, there's this issue of compositional reasoning of state machines while also providing a refinement proof, right? We might be able to prove that the model itself is correct, but we want to also ensure that the C implementation upholds those properties we've tried so hard to prove. So to this end, we've developed the Q framework, and I might just refer to it as Q. Q framework is a little bit less ambiguous if you Google, to address this gap and provide a mostly automated refinement proof into C. So just brief structure, I'll talk, inspired by Laura, I suppose, I use a secure coffee maker. I think it's a good example for computer scientists. And there's a lot of interacting components, so I'll talk about those. I'll describe our refinement arguments, and then I'll give a little bit of our formalization in Coq, and then I'll talk about conclude. So there's a lot going on here. I'll step through the bits piece by piece. Essentially, we can think of this workflow as something that flows from the top left down to the bottom. And so one thing to keep in mind is the blue are things that are Sandia. Obviously, Sandia did not develop Frama-C. Now, the double struck lines, these are things that are the manual parts of this. So we're writing the C by hand. We're ensuring that the style is obeyed and compatible with our internal representation by hand. But other than that, most of this process is automated. So again, don't worry too much about it. I'll step through it piece by piece. So I'll first talk about the modeling languages. And if you've ever used Stateflow before, this is sort of what they look like. The text is a bit smaller. I'll zoom it in a bit. There's some states, and they're interacting. And you can see here, there's guards along the transitions. But from here on out, I'll be talking in a more abstract sense. We have some coffee machine that you push a confirm or cancel button, and it brews for some amount of time. Don't worry too much about this, but I just wanted to show this to indicate that there is some state labeled transition system, and we have some composition. So we can imagine the composition in parallel with some sort of payment system, which just inserts a coin and presses continue over and over again. Right. Okay, so imagine we have some model, and we have models of many different interacting systems. We want to write some properties about these models. So here's the system again, and what we use are LTL and CTL because of their wide support. LTL, linear temporal logic, CTL, computation tree logic. One might think of some like example safety condition, which says the coffee maker should not be confirmed after coffee is done brewing. So we can notice that the brew equals 2 condition is when the coffee maker is done. That variable is set to 0 when you go back to the ready condition. So we have this property, but we use NuSMV as our backend for model checking to ensure that these properties, whichever ones we might write, are upheld. Now I'll talk a bit about now what we're doing here is we're generating. We have the Stateflow model. We convert this into a representation that's convenient for us to work with. There's this XML here, which is we call this format QSpec. It's basically a state chart XML format. They're not written by hand, so they're very verbose. Essentially, we're translating from MATLAB, so we write this parser for MATLAB. One interesting feature of this is that we can go in the reverse direction. So suppose we have this NuSMV model checker finds a counterexample. The QSpecular can generate this as a Stateflow test case. So this is this sort of hints at the collaboration we have between the system designers. Give them a Stateflow counterexample. We can refine the model, rewrite these properties. So this is very useful for our case. Now, okay, so we have a Stateflow model. We have some properties. Now there's the C implementation. We have a restricted subset of C. One example is we need only one observable for a function call, for example, based on the state of our tool. The other thing we require is a map from Stateflow, all the variables used in Stateflow, into C. We call this a simulation map, and I'll refer to this later when I talk about the refinement of our model. Other thing we require, which is sort of a reasonable assumption, which is to separate hardware accesses, for example, memory mapped I/O or volatile variables into function calls. Now, there's actually other issues with this. It's generally a good idea to separate volatile variable accesses and function calls anyway because of potential miscompilation. But regardless, we assume that we have some axiomatization of the hardware that we write in Frama-C. And if you've never seen Frama-C before, the @ symbol means you have some sort of Frama-C annotate or ACSL annotation, the ANSI C specification language. And here we have some volatile variable V, and we say once this is read from memory, we keep this trace of all of the values. So we have this observable T, which means we have this trace of all the values that the volatile was read into. And so these ACSL specs are used in our soundness argument. Okay, now I'll kind of talk about, this is at the center. This is a little bit, in some sense, the main part of Q. Is the QLang, which is our compiler. So to recap a little bit, we have QSpec, which is our internal representation of a state machine. We have a C program written into constrained style. We have the simulation map from Stateflow and C variables, which is really just a JSON file, but it maps these variables the same. What happens in QLang is it flattens the SMV model. I'll describe what that means. And it outputs a C header file with this annotations, which is to say all of these LTL properties of our model are now mapped onto the C implementation. So these are requirements that if they uphold in the C, then the model, and there's some refinement between, or rather, the C implementation refines the state machine model. QLang also has several backends. We'll focus on SMV. I want to talk a little bit about flattening, right? So our Statecharts support parallel and nested composition. However, we expand that out so that there's none of that. Now, what happens, we see here just 3 states, we get an exponential increase in the number of states when we do this flattening. The benefit of this is it's a simple implementation that allows us to reason about this and allows us to interface with NuSMV. The problem is this exponential size increase. How to solve this is future work. One potential example is to pass the buck on to NuSMV, but NuSMV still has to deal with exponential size increase. Another potential future work would be with some assumed guarantee reasoning, which I'll get into a little bit if time permits. All right, so now that I've talked about the sort of the QLane compiler, I'll talk a little bit about some tricking we have to do. We do a little bit more post-processing to the C source code, and I'll describe the motivation, right? So we have this tool called QFact, which is a Clang tool which annotates a C program with its spec. The question might be, well, why is this necessary? If we can think of an ACSL annotation as just a header file, well, the C semantics are complex, and there's just many. If the software engineers write the C code, there's a lot of implementation defined or unspecified behavior. One example would be, what is the order that function arguments when passed in are evaluated? So we use a little trick here. We convert from C into C Lite and then back to C. So C Lite is a applicative normal form subset of the C language that is used in the CompCert compiler. There's a forward translation. Fortunately, we modify, we have a branch of CompCert, and we modify this to do the reverse, so we get the backward translation back into C. We do this because it simplifies dealing with the developers. They're not looking at a C-like code. I think. Oh, okay. Yeah, and so right. So that essentially that is the framework. I didn't really talk about the backends, but once we have the ACSL annotations, we can dispatch this to Frama-C, and it runs various. Now there's actually a hidden arrow here. I lighted for space, which is to say Y3 handles this. But regardless, another thing we do here is this is more of an engineering effort, but it still, I think, provides some interesting feedback, which is Q workflow. So again, consider our situation. We have Microsoft Word files with requirements written on them in English, and we have some identifier. We have the Stateflow model, and we have the C code. Now, what we can do here is run the analysis and generate the counterexample, and then link both the status of the proof as well as the potential counterexample back into the requirements documents. So this is very helpful for this iterative workflow we have. So now I'll talk a little bit about our refinement argument, and to state again the goal of Q framework. Our goal is to prove system-level temporal properties about asynchronously interacting components. So first, we prove that the properties hold for the Q specs, which are the our internal state machine representation. Then we prove a given C program implements or refines a component of the Q spec. I've talked about step 1, but and we use this with NuSMV. Now I describe a bit of step 2, because given these generating these ACSL function contracts and using Frama-C to prove this, we have to very carefully choose our notion of refinement from the model to C to ensure that this is sound, because there are the C semantics are subtle, as well as we want to make sure that there is this correspondence. And I won't get into all of this, but essentially we're proving a weak simulation, which is to say, provided that the program terminates, we have this property. And so I'll step through a little bit of what is going here. I apologize for the notation. The Q here is not Q framework in general. This is, think of Q as an abstract model, as a Q spec file. So if we have some labeled transition system Q, and we have some labeled transition system P sub C, which is the concrete implementation. We have this phi, which is the simulation map. And here, we're essentially forming a Galois connection here. So we label the actions of this state Q as observables in the model. So you might, if this is a traditional LTS, you might see these labeled as A, but observables. We have this transition relation, and then we have relations over the states in Q. And then we have this refinement. So in order to do the refinement, we have to handle a Frama-C ghost state to get to handle this these observables, which you can think of the environment or volatile variable axis. I'll get into that later. Then we have the C program state transformer semantics. So provided you can think of the C running a C program as a label transition system, which that is, I'll get into that. And then we have these relations over the C program state. So this is essentially the Galois connection. Provided we can think of P sub C as a transition system. Now, again, this is not a trivial thing to understand. So put a different way, so essentially I'll give you the trick, which is to say we have our abstract model Q, and we have our concrete model P sub C, and we asynchronously compose these both with things that are models to each other. This is how we get the refinement. So the volatile environment, we can think of this as essentially a label transition system with a single state, and which represents the environment, and all the observables, these transitions being modifications of a volatile variable or memory map IO or whatever hardware you might want to do. This is the argument of our refinement. Okay, so that's, again, I really roughly sketched out the proof, but maybe that gives a little bit of intuition. I'll talk a bit about our formalization in Coq. And so we have the semantics of our state machines, or of our Q specs, which is a model of what we've implemented in Q framework. Q framework was written in Haskell, so that we don't have this extraction or some verified implementation. However, you can see here that the machine and the chart are relatively simple, where we have some state and environment. We also approve in Coq refinement between two types of state charts. Now, we don't have the whole C semantics, but it's still useful to reason about these sorts of things. I'll give one example here of what we've used the Coq formalization for. Now, what we're stating here is some property of nesting of state charts, right? Because it's not always clear that the nesting is sound. If we have some nested state charts, because we have to have some sort of way to link up the state charts once you've taken a step inside the nested one. So informally, we have the notion in which case this is sound, which is to say, if we have a top-level state machine, which steps from maybe some state A into B, then the nested, we must require that the inner state machine also steps from A to B. It can't do some like twiddly stuff while it's waiting. This is like the restriction in order to get nesting, which doesn't hold in all state machines, but this is one sort of example of some useful result we can get. As I briefly, I think I mentioned this Q framework is compositional over parallel composition. This is a sort of a simpler notion, but then this is the case in which nested composition is compositional. It's a weird way to write it. All right, so I've sort of briefly gone over the Q framework. I'll talk about a little bit of related work. The work that we're, I suppose, most inspired by is the DeepSpec project and the verified software toolchain that came as a result of this. Now, this provides the strongest assurance arguments because it has a full program logic for C in Coq. Now, the problem with this is it's very time intensive. It's also a brittle, which is to say you change the C program, you get your proof will likely not work. Now there's some work in proof repair, but this is in our experience, using VST is more time intensive than we are able to do. So other related work is there's modeling with Event V, SMT, TLA+, which I've sort of mentioned before. Probably the most similar work to us is Trillium, which is a new project which is proves a proof of refinement in COC between TLA+ specs and this DSL they use for specifying concurrent systems called a narrow-sliding. So we do the same thing, but we're not formalized in COC, and we are our target is the C language. Some future work I want to describe is the multiple observables per function call. I'm missing. Okay, multiple observables per function call, and the size of another issue is the size of the flattened Q spec is this scalability concern. So one would hope that the modularity of the system designs would allow some modular reasoning. Of course, you can fall into pitfalls here. One of the plans we want to work with is use a assumed guarantee reasoning, or maybe the circular assumed guarantee reasoning. We don't have a formal proof of compilation. I think that's an interesting research that we can look into. A few restrictions on the C implementation. This makes it easier for the software engineers we work with, as well as automatically generating some ACSL specifications. For example, pure functions. We need to have these, but they're not very they don't affect the environment, and so the verified software toolchain has some symbolic executor. So this is something else we can look into. Anyway, so in conclusion, the Q framework allows us to build compositional reasoning and provides evidence that C refines a given state machine model. It has a little bit strict limitations on the structure. Our future work is this one QED, which is to say a single proof of correctness from the high level specification all the way down to the hardware. Our tool is not open source, but I have some examples of the code here. And so that concludes my talk. I'm a little bit quick, but yeah, that concludes my talk. Thank you all for listening.
Thank you. Questions?
Thank you for that. I have one question on the undefined behavior analysis. Have you looked into the EVA plugin method for Frama-C, which is a composition tool that aims to prove the assumption for undefined behavior? Have you looked into it?
So I've used EVA plugin a little bit before. Now we sort of, I don't want to say we gloss over this, but when we translate from C-Lite to C, I think it removes a lot of, doesn't remove undefined behavior, but it removes a lot of the issues that we have. Now, I think that this is a good idea to do, is to really have a bulletproof argument of the C implementation, no undefined behavior, because there's all these potential issues of how volatiles can be compiled and things like this, especially that can happen because of undefined behavior. Yeah. Also realized I think I had an older slide. I used an older slide deck, so I didn't explain the ghost state, but it's in there.
I have a question regarding the flattening. Is this necessary, or is it because it's maybe faster? Because you can have multiple so-called modules in NuSMV, which are parallel state machines that are then composed. So you don't really have to flatten it before you hand it over to NuSMV. So why did you choose to flatten it?
So, well, we chose to flatten it because that's, this is not my expertise. I'm not 100% sure that we know the precise semantics of our nesting and composition is the same as what NuSMV expects. But once we have established that, yes, we will. This is what we'll do. Is because one would hope that NuSMV it's a very mature tool. It has many different ways it can optimize. It can be more clever about simplifying these nested or parallel composition better than we can, which we do a very naive flattening. We just expand out as everything.
Yeah, I know it can be done. I don't know how efficient it is, but I have an example where I can show you one way it can be done later.
Oh yeah, thank you.
Other questions? Then maybe a quick final question, unless there are more. Is there a chance the tool will become open source at some point in the future?
Politically, I hope so. We've tried unsuccessfully in the past. The way Sandia National Labs works, there's many like privacy concerns. Stay tuned. Maybe in a couple years. Yeah.
Okay, that'd be great.
Yes. I'm very curious about the specification language. So currently it looks like just LTL or CTL with some state checking. Is that possible to add on maybe trace properties? Our LTL is already traced. Well, is that easy or flexible for you to add other logic into your specification?
So the question is it, can we extend this specification language to be more powerful, not just LTL? The proof of refinement, I believe, relies. I don't think the proof of refinement relies on exactly which logic we use. However, sorry, let me take this back. The proof of refinement does rely on the logic we use, which is to say our backend for SMV is required. Now, if we would to choose some logic like TLA, I think that we might be able to have a more powerful thing, but it's highly not trivial because we care about soundness, and we want to make sure that whatever we're writing in the specification can actually be fully represented.
Will you be working on that direction to the extent?
As far as I know, I think that adding more backends, which is to say we could add more logics, it's not our first priority. I think our first priority is to have greater structure on, or more expressive programs that we can write, for example. So I think the limitation now is not the state machine. The state machines are not the limitation. The limitation is what C programs that developers want to write can be expressed with these state machines. So I think that's the priority for us, instead of adding more expressive logics onto this. However, another example here is with Frama-C, what it can check. These, we write some Frama-C and it may or may not be true, but then it oftentimes, this automation issue of can Frama-C dispatch as proof? Is it because of some issue with program itself, or is the issue, right? This is always a problem with verification. And so I think these are the issues that we're focusing more on, as opposed to a more expressive specification logic.
That sounds more practical as well.
Yeah, and so this is like in industrial, I guess, use case, right? And so, yeah. Good question, thank you.
Okay, let's thank the speaker again.